Welcome to this explainer. Today, we're jumping straight into the complex math of machine learning and transforming it into a genuinely fascinating journey. Out of the deep black void of raw data, we're going to illuminate the logic of how algorithms actually learn to predict the future.
Right off the bat, this is the fundamental question of supervised learning, and it's an incredible concept when you really think about it. We essentially hand an algorithm some labeled input data, which we call features, and we ask it to go find the hidden relationship to the correct output or the label. The entire goal here is for the machine to learn this relationship so incredibly well that it can make highly accurate predictions on entirely new, completely unseen data.
Here is our roadmap for today. We'll start with a welcome to supervised learning, then we'll move on to drawing the perfect line and descending the error mountain. After that, we'll tackle the complexity trade-off, evaluate the machine, and wrap it all up with the complete regression workflow.
Section 1. Welcome to Supervised Learning, teaching machines with labeled data.
Before we go any further, we really have to draw a strict boundary here. On the left side, shining in cyan, we have classification. That's all about predicting discrete categories. Things like whether an email is spam or not spam, or guessing if a song is rock or pop. But today, our focus is entirely on the right side, highlighted in purple, regression. Regression is all about predicting continuous numbers. We use it when we want to predict a house price, tomorrow's exact temperature, or a future salary.
Section 2. Drawing the perfect line, the birth of linear regression. Let's look at something we all love, coffee. If we look at this simple data representing coffee brewing, our model intuitively picks up on the trend. As brewing time increases from 2 minutes up to 6 minutes, the caffeine extraction goes from 45 milligrams up to 125 milligrams. The algorithm attempts to draw a regression line to estimate this exact relationship. It calculates a slope that tells us precisely how strongly the brewing time affects the caffeine punch. It's essentially finding the mathematical geometry of a perfect cup of coffee.
Section 3. Descending the error mountain, confronting our model's mistakes.
Now, the real world isn't a perfect straight line, so our model inevitably faces a problem. Its predictions are never completely perfect. Enter the residual. This is essentially the main villain our model has to learn to defeat. Every single time the model makes a guess, the residual is sitting right there to point out exactly how far off it was.
Let's ground this with a concrete example. Say our model predicts a salary of $4,700, but the actual salary is $5,000. That $300 difference, that is our residual. The algorithm's ultimate mission is to minimize these total errors across all the predictions it makes. But here's the catch. It doesn't just simple-mindedly add them all up.
So why do we use mean squared error? Why square them? Well, the model does this to aggressively punish its biggest mistakes and to make the math smoother to solve. Think about it. By squaring the residuals, a negative error and a positive error won't accidentally cancel each other out to 0, which would trick us into thinking the model is perfect when it's not. Plus, an error of 2 just becomes 4, but a massive error of 10, that blows up into a penalty of 100. And crucially, squared functions create these beautiful, smooth mathematical curves, which is absolutely vital for the very next step.
To minimize those squared errors, the model uses gradient descent. This is an optimization algorithm that is literally like descending a mountain while blindfolded, simply by feeling for the steepest downward slope with your feet. You can't see the whole landscape, right? So you just feel which way is down, take a step, and repeat. In machine learning, the gradient points the way, and the algorithm steps downward until it finds the absolute lowest valley of error.
Now, the size of those steps you take, that's controlled by your learning rate. And you have to be careful, because if it steps too wildly, it will completely overshoot the valley and fail to learn anything. Set the learning rate too small, like 0.0001, and the descent is agonizingly slow. A rate of 0.01 is pretty common. But push it all the way to 1.0, and the algorithm takes steps so massive it literally bounces out of the valley, making the whole model totally unstable.
Section 4. The complexity trade-off, adapting to the real world.
As our model graduates to complex, nonlinear real-world data like plant growth, which sprouts super fast and then slows down, it uses polynomial regression to curve its lines. But this introduces a massive new danger. We absolutely have to avoid the extremes. You've got underfitting over there in purple, where the model is way too simple and rigid to capture the real patterns, and then you have overfitting over in cyan, where the model is given so much flexibility that it literally just memorizes random noise instead of learning the true underlying trend. Our goal is to hit that sweet spot perfectly in the middle.
I love this quote because it brilliantly illustrates the danger of overfitting. If you give a model too much complexity, it will perfectly fit pure nonsense just to look correct on the training data. As the famous mathematician John von Neumann pointed out, give an algorithm enough parameters and it will just memorize the data points, perfectly tracing an elephant's trunk rather than actually learning anything useful for the real world.
Section 5. Evaluating the machine. Measuring true quality.
To guarantee our model hasn't just memorized the answers, we use k-fold cross-validation and some strict mathematical metrics to grade its performance on data it has literally never seen before. We test it using mean squared error to catch the big mistakes and mean absolute error to avoid getting tricked by wild outliers. We also look at root mean squared error because by taking the square root, we bring the error right back into the exact same units as our target variable. That makes it incredibly intuitive to understand exactly how far off our predictions really are.
But honestly, the easiest grade to read is the R-squared score. It's like a straightforward report card where a 1.0 is totally perfect. An R-squared of 0.8 means your model is doing great, capturing 80% of the variance in the data. But if you see a 0, your algorithm is literally no better than just predicting the average every single time. And anything below 0, yeah, your highly trained machine is doing worse than just blindly guessing.
Section 6. The complete regression workflow, putting it all together.
Let's zoom out and look at the big picture. This is the exact workflow every professional ML model goes through. It's the foundational architecture of AI. We start by collecting raw data and preparing our features. Then, we choose our regression model and train it, sending it down the error mountain using gradient descent. Finally, we strictly evaluate it with our metrics like MAE or the R-squared score and apply techniques to ensure it definitely hasn't overfit the data.
So representing relationships, measuring errors, optimizing parameters, and generalizing to unseen data. This is the beautiful structured reality of how machines predict the future. We've journeyed all the way from simple scatter plots to the blindfolded descent of optimization, all to answer that one fundamental question. The math is clear, the workflow is proven, but the truly exciting part is what comes next. What unknown are you going to predict?